Alright, SM3, so hopefully you are coming from 1.1, where we talked about modeling with area. Now we're going to talk about modeling with volume. Um, so we talked about population density, which deals with area of a given land. Now we're going to talk about just density in general, which usually means you're using volume. So density is the amount of matter that an object has in a given unit of volume. In a given unit of volume. Okay, so if you have a cube, so in this cube, what density tells us that in this cube, pretty much how much matter is in it. So, and matter we use as mass. So how much mass is in a given cubic unit. So that's how we find density, is we take the mass of an object and divide it by the volume of an object. Okay, now mass is usually, whenever we're talking about density, mass is measured in grams or kilograms. And volume is measured in centimeters cubed or meters cubed. Okay, so we're saying in a given cubic unit, how much matter is inside that cubic unit. So that's what density tells us. So let's go ahead and dive right into it. Let's find the density of this gold bar right here. So the diagram shows the dimensions of a standard gold bar at Fort Knox. Gold has a density of 19.3 grams per cubic centimeter. Find the mass of a standard gold bar to the nearest gram. So first things first is notice that these dimensions are in inches. Now if we want, we actually want to, change so that we are in centimeters. We want our volume to be in centimeters or meters. So let's change these to be in centimeters. So first know that inches, so for 1 inch, this is equivalent to 2.54 centimeters. Okay, so that means what we do is we can take 7 inches, and to find out how many centimeters are in it, we need to multiply it by 2.54 centimeters, because for every inch there's 2.54 centimeters. So we do 7 times by 2.54. And we get about 17.78. So this side length is also 17.78 centimeters. Okay, now for 3.625 times that by 2.54 centimeters. Okay, when you do that, you should get something about 9.2. So 9.2 centimeters. And then 1.75 inches, multiply that by 2.54 centimeters. And when you do the math there, you should get 4.45 centimeters. Okay, so now that we have this all in centimeters, let's find the volume. Now, to find the volume, we just need to multiply the length times the width times the height of this gold bar. So multiply all three dimensions together. So we can take 17.78 times that by 9.2 times that by 4.45. And when you do all of that, you should get something close to 727.7, something like that. But let's go ahead and make sure. I think it's something like that. If I remember correctly, 17.78 times by 9.2 times by 4.45, and yeah, so 727.9. Okay, so that's centimeters cubed. So that's the volume. That is the volume of our gold bar. Now, let's finish reading what we have. So gold has a density of 19.3 grams per cubic centimeter. Find the mass of the standard gold bar to the nearest gram. So we want to find mass, and you see that it gives us the density, and we just found the volume. So the density is 19.3. Well, first of all, let's break this down a little bit. So density is equal to mass over volume, but we want to find the mass, and so in this case, mass would equal density times by volume. Okay, so we take the mass of the, we're looking for the mass, and we take the density, which was 19.3 grams, and we multiply that by the volume, which was 727.9. 27.9 centimeters cubed. Okay. So then, whenever we do this, multiply this together. So we got 19.3. So that times by 19.3, and we get, whoops. I think I just took the wrong thing again. So take that and multiply that by 19.3. And we get 1448. 14048. So this would be grams. Yep. Oh, whoops. Also, these units should be per centimeters cubed. Okay, so so density, this is density. Density is grams per cubic meter, so grams per cubic meter, and then volume is by cubic meter, so that whenever you multiply these will cancel, and you'll just be left with grams, which is how you come up with the correct unit. Okay, so there you go. The mass of this gold bar is 14,048 grams. Alright, let's do 2 more of these problems. So in here it says a tree harvester is often interested in the volume of a tree's trunk because most of the wood volume is located there. A tree harvester estimates the trunk of a sequoia tree to have a height of 50 meters and a base diameter of 0.8. So let's take a look at this tree trunk, which would be kind of like a cylinder. He says that the average is 50 meters, and with a radius or a diameter of 0.4. So I'm more interested in the radius. So the radius here would be 0.4 meters. Okay. So the wood of a sequoia tree has a density of 450 kilograms per cubic meter. So I know that density is equal to 450. And we want to find the mass. So again, we want to find the mass. Mass is equal to density times by volume. We have the density, we just need the volume of this object. So this is a cylindric object. So the volume of a cylinder is it's pi r squared times by the height. So in this case, it would be 50. So this is the volume of a cylinder. So find the volume of this right here. Volume is equal to pi times by the radius, which was 0.4 squared, times that by the height of the cylinder, which is 50. Okay. And when we do that, we should get a volume of about 25 25.13 meters cubed. Let's double check though. So 0.4 squared times by pi times by 50. Yep, 25.13. And we're looking to find the mass, and mass is equal to density times by volume. So in this case, mass would be equal to the density of the object, which is 450 grams per or kilograms per cubic meter, and multiply that by the volume. So our volume was 25.13 meters cubed. The units for meters will cancel, leaving us with kilograms. And 450 times by this, so multiply that by 450, and I get 11,309. So 11,309 kilograms. So that's the mass of this trunk. Okay, let's do one more. Now, if you remember from the previous notes, in this example problem, we talked about how if we take dimensions of an object and cut it in half, we learned that this doesn't mean that the surface area is cut in half. So we're going to see if the same thing applies with volume. Okay, so it says here, before a winter storm, a pile of road salt has the dimensions shown. After the storm, the linear dimensions of the pile are 1/2 of the original dimensions. Okay, so how does this change the effect of the volume of the pile? So basically, let's find the volume of this pile. We need to find the volume. Now this is a cone shape. Okay, for a cone, volume is equal to 1/3 pi r squared times the height. So 1/3 pi r squared times by the height. So we need the radius of this cone pile. So we see here that we have the diameter as 90, which means it will have the radius of 45. So from here to the edge, this should be 45 feet. Now the height would be represented right here. So that would be the height. Now we don't know the height, so we need to find the height first of this cone pile of salt. So you should notice that this makes a triangle. The slant of this sand pile is 53, and so this is the height. So I'm interested in finding the height. And since this is a right triangle, I can use the Pythagorean theorem to solve. Okay, so I know that height squared plus 45 squared should equal, I think it was 53. Yeah, 53 squared. And if we solve for the height would be equal to the square root of 53 squared plus 45 squared. So that's how we can find the height. So do the square root of 53 squared plus 45 squared. I'm pretty sure something's off right there. So square root of 53 squared. Oh, that should be subtract. It should be subtract. There we go. Sorry, that should be subtract. Okay, and this will equal 28, like we have here. So the height of this pile of sand is 28 feet. Okay, so now that we have all our required dimensions, let's find the volume of this pile. So volume is equal to 1/3 pi times by the radius squared times by the height. So what does this come out to be? So for me, I'm going to do pi times by the radius squared times by the height. Take this and divide it by 3. Okay, and I get 59,376.1. So that's the volume of this pile right here. But we're interested in how the volume is changed from before and after the sand pile. So it says after the storm, the linear dimensions of the pile of road salt are 1/2 of the original dimensions. Okay, so that means that after the storm, this would be 14 feet, and this would be 22.5 feet. Okay, so let's find the volume of that object. So volume is 1/3 pi times by the radius squared times by the height. Okay, and this would be the volume of the pile of sand or pile of road salt after the storm. So let's see what this comes out to be. So pi times by 22.5 squared times by the height, which would be 14. Take that amount and divide it by 3, and I get 7,422. Okay, now to compare, how does this change affect the volume of the pile? So we know that the dimensions are halved, but let's see the ratio of these two objects. So if we take the volume of the smaller and divide it by the volume of the larger, 59.376.1. Okay, so we take that and we divide that by this value right here, and we get 0.125. So that is the volume of so that's not the volume. So this is the volume of the smaller, this is the volume of the larger. When we find the ratio between the two, it's equal to 0.125, which is 1/8. It's 1/8. So again, just showing that just because the dimensions are half doesn't mean that the volume is also going to be half of it. Okay, so that's what we're trying to illustrate here. Okay, so just as an extra practice, just to get you a little bit more practice, we'll do part of number 2. The rest of these problems, like right here on this page and on this page, you should be able to do if you followed closely enough with the rest of the example problems. They all follow pretty much exactly. But in any case, so for this one, it says before 1965, dimes and quarters were made of silver. The density of silver is about 10.5 grams per cubic centimeter. Find the mass of the coins given their dimensions. So we want to find the mass. And remember that mass is equal to density times by volume. So here it gives us we know that the mass of the object, or the density of silver, sorry, not the mass, the density of silver is 10.5. So we have the density of our object, but we do not have the volume. So that's our goal, is to find the volume. But we are given the dimensions of the dime. So if we have our dime, here's our dime, and it says it has a diameter of 1.79 centimeters, but I'm interested in the radius, so I'm going to do 1.79, divide that by 2, and I get 0.895. So radius is equal to 0.895. And the thickness right here is 0.135 centimeters. So can I find the volume of the object? Remember that. So this is pretty much a cylinder right here. It's just it's not thick and it's very small. So the volume of this would be 2 pi, not 2 pi r squared, it would just be pi r squared times by the height. Okay, so we can find the volume of the dime by doing pi times by the radius, which is 0.895 squared times by the height. Okay. So, whoops. So that squared times by 0.135 times by pi. I probably need to make sure that I'm typing this in right, getting ahead of myself. Okay, so we do pi 0.895 squared. So pi times by 0.895 squared I'm just messing all this up. 0.895 squared, and that times by 0.135. Okay, so I'm getting yeah, 18.64. So 18.64. Yeah, I keep messing up. That shouldn't be divided by. Sorry, I don't really like this calculator app. The buttons are really small, so I miss them a lot. So times by. There we go. Okay, so it was what we had before. So I was going to say that sounded way too large of a volume for just a small dime. So 0.34 is what the volume should be. So 0.34 centimeters cubed. That's the volume of our object. Now to find the mass of the object, we need to take the density, which was given to us as 10.5, multiply that by 0.34, and that gives us the mass of our object. So that times by 10.5, and we get 3.57. So 3.57 grams. So that is the mass of a dime. Okay, now go ahead and see if you can do the same thing with the quarter. Find the mass of the quarter here. Okay, and that should pretty much do it for all of 1.2.